Alright, this is going to be a little dangerous because we're going to try to repeat it from memory. But hopefully we can do it. So, he started with this. One, boy. So, our marker died in the middle. That was not the problem I was expecting to come up. Minus 1, plus 1, minus 1, plus 1, dot, 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 equals a half. Alright, so what was the argument here?
Well, if you stop at any place along this, you're going to get either, if you stop at an odd place, you're going to get 1. If you stop at an even place, you're going to get 0.
Okay.
But you don't stop, so you just take the average.
Alright.
And that's 1/2.
Okay. What do you think, Wood?
Yeah, that's what this argument.
Okay, and then a common thing you might see, you've definitely seen this, you'll probably see this later, 1 plus x squared plus dot dot dot, this equals 1 over 1 minus x, this series.
Mm-hmm.
And you can see if we set x equal minus 1, here we'd get 1 minus 1, plus 1, minus 1, plus 1, dot dot dot, and that would equal a half. So maybe this makes sense, maybe somehow or other that makes sense. Okay, and then what did he do next? What did he do from this series? After he showed that we could think about this series as having a value of 1/2.
Well, he called this series, it was S1.
Alright, so this is S1.
And then he had another series called S2.
What was S2?
That was 1 minus 2 plus 3 minus 4 plus 5 and so on.
And he was trying to figure out what that was.
So what he did to figure that out, what he did was he sort of added he added 2 copies of it together.
Okay, so he put another one, S2, and he started at 1 over 1, so he wrote it like this: 1 minus 2 plus 3 minus 4 plus 5, dot, dot, dot.
Yeah.
And he said, look, if I'm going to let this be something, I'll just call x, and then when he added it together, he got 1, minus 1, plus 1, minus 1, plus 1. This is 2x.
But this is S1 here, and we know what S1 is.
It's
so
a half.
It's a half. So half equals 2x, so x must be a quarter.
So this was a quarter. Is there anything about this proof here that seems suspicious to you?
Well, the only thing that is suspicious is the shift, but I think since both are infinite, I think that it's allowed.
Okay.
Yeah.
All right.
Since you're not, like, there's not going to be some number at the end of this that doesn't get added to anything.
Okay. One of the things at the talk at MIT on Thursday was about these kinds of shifts when you're talking about with infinite series. So you are right to be suspicious of that shift. It's interesting that those shifts with infinite series can create problems, but glossing over that problem. So this series was a 4th, and what was his last step?
So his last step was he did the 1 plus 2 plus 3 series.
S3 was 1 plus 2 plus 3 plus 4 plus 5 plus...
And then he subtracted this series.
So I'm going to call this x again, even though I've already used x once. Okay.
He subtracted this series S2 away from S3.
Okay, so then that would be x minus a 4th. Oops, x minus a 4th. I'm going to take this series and subtract that series?
Yes.
Okay, x minus a 4th.
And then, see, when you subtract, the 1s go away.
Okay, so I get 0.
Plus 4.
Plus 4.
Plus 0.
0.
Plus 0.
Plus 8.
Plus 8.
Plus 0.
12.
Okay. And this is 4 times...
It's 4 times S3. So 1 plus 2 plus 3.
We get rid of the zeros. Does that bother you?
Not really. They all equal 0.
Okay, but it still creates a shift, right? So we're we are doing some shifting.
We're
but anyway.
shrinking, but it's still infinite.
So that's x though, right? So this is 4x. So now I have 4x equals x minus a fourth.
So 3x equals minus 1/4, so x equals minus 1/12.
X equals minus 112. Alright. That's their whole proof. Alright, and so now we're going to go on to one last thing. Okay?
Alright.